This is lesson 83 of physics. In today's lesson, we're going to be looking at collisions and the kinetic energy of collisions. But let's begin by working out a bell work problem.
A 36-kilogram child slides down a playground slide that is 2.5 meters high. At the bottom of the slide, she is moving at 3.0 meters per second. How much energy was lost as she slid down the slide? So I know that my initial kinetic energy plus my initial potential energy should be equal to my final kinetic energy plus my final potential energy plus any energy that is lost. In this particular case, my initial kinetic energy is going to be 0 because my initial velocity is 0. I'm going to assume that my final potential energy is 0 because I'm assuming that the height at the end is at the ground level, which would be 0. I'm also assuming that my initial velocity is indeed 0. So what I'm going to do is I can ignore the initial kinetic energy because it was 0, and I can ignore final potential energy because it was 0. So that gives me my initial potential energy, which is mgh, being equal to my final kinetic energy, 1/2 mv squared, plus any energy lost. In this case, I cannot cancel out the masses because I'm trying to figure out how much energy was lost. And so even though if it weren't for this ending E value, I'd be able to do that. But since I'm looking for the energy lost, there is going to be a mass portion involved in there, so I can't cancel it all out. So substituting in, I have the mass of 36.0 kilograms times gravitational, which is 9.80 meters per second squared, times the height of 2.5 meters. That is going to be equal to 1/2 my kinetic energy, which is the mass of 36.0 kilograms, times the final velocity of 3.0 meters per second squared. So multiplying out, I get over on this side 882 kilogram meters squared per second squared, which is joules. And that is equal to, if I take 1/2 of my 36, that gives me 18. And then if I multiply by 3 squared, which is 9, that gives me 162. And that would also be in joules, plus the amount of energy lost. So subtracting 162 joules from both sides of my equation, I get 720 joules. Now with sig figs over on the left side, I have 2 significant digits. And then over on my right side, I'm also going to have 2 significant digits. So I can round to the nearest 10, which is what I've done. So my final answer is 720 joules.
Question 16 says, suppose that a bike rider, the one in problem 15, pedaled up the hill and never came to a stop. In what system is energy conserved, and from what form of energy did the bike gain the mechanical energy? Well, if we consider the system, the earth, the bike, and the rider, the energy has to remain the same. However, the energy is not all mechanical energy at the end. The rider had to be considered to have some sort of stored energy, such as in the form of chemical energy like food and energy in his muscles, that was converted into the mechanical energy.
A skier starts from rest at the top of a 45-meter high hill, skis down a 30-degree incline into a valley, and continues up 40 meters on the next hill. The heights of both hills are measured from the valley floor, and assume that you can neglect any friction and effects of the ski poles. How fast is the skier moving at the bottom of the valley? Well, since we're neglecting any type of friction, we're going to be able to assume that we have no loss of energy. So my potential energy at the beginning should be equal to the kinetic energy at the bottom of the valley. Potential energy is mgh, kinetic energy is 1/2 mv squared. I can cancel out my masses in this case, and that gives me my gravity, which is 9.80 times the height of 45 meters, And that should be equal to 1/2 the velocity at the end being squared. If I take 9.8 and I multiply by the 45, I'm also going to go ahead and multiply both sides by 2 to get the v squared by itself. That gives me 882 joules is equal to my velocity squared. If I take the square root, I get an answer of my velocity being approximately 29.698 meters per second. And in this case, over on the left-hand side, I have 3 sig figs. The 1/2 is exact. And so when I take the square root, I can end up with three significant figures as well. So my final answer should be 29.7 meters per second. Now for the second part of this question, what is the skier's speed at the top of the next hill? At the top of the next hill, it's only 5 meters less than the top of the first hill. So I can assume that really just my change in my height is 5 meters. So if I take the 9.80 meters per second squared and I multiply by the 5 meter difference, that should be equal to the 1/2 times the final velocity squared of my skier. So once again, if I take 9.8 times the 5, that gives me 49. I'm going to go ahead and multiply both sides by 2. That gives me 98 equal to the velocity squared. Taking the square root of that, I get approximately 9.899 meters per second. And here I'm limited to only 2 significant digits, so my final answer is 9.9 meters per second. And then the final question, do the angles of the hills affect your answers? Well, it does not, since we're considering that there is no friction. In reality, if there were friction, then those angles would have somewhat of effect on how quickly I'm going up and down the hills. In a belly flop contest, the winner is the diver who makes the biggest splash upon hitting the water. The size of the splash depends not only on the diver's style, but also on the amount of kinetic energy the diver has. Consider a contest in which each diver jumps from a 3-meter platform. One diver has a mass of 136 kilograms and simply steps off the platform. Another diver has a mass of 102 kilograms and leaps upward from the platform. How high would the second diver have to leap to make a competitive splash? So I've written down the information that we know. We know the heights of both initially are going to be 3 meters. However, the height of the second person, since he is leaping upward, is going to change. The mass of the first individual is 136, and the mass of the second is 102. So what I'm going to do is I'm going to find the kinetic energy of the first diver. Now, in order to do that, I need to find out, well, what is his potential energy? If we're neglecting any type of friction, the potential energy at the beginning should be equal to the kinetic energy at the end. So if I take mgh to find this individual's kinetic energy, I would get the mass of 136 kilograms times the gravitational constant of 9.80 times the height at which he jumped, which was 3 meters. And so his potential energy, which is going to be equal to his kinetic energy at the end, is going to be 3,998.4 joules. I would be limited to 3 sig figs in this case. Now, I want the second diver to have the same amount of kinetic energy, which means he's going to have the same amount of potential energy. Well, since potential energy is equal to mass times gravity times the height, the mass I know is 102, gravity is 9.8, and so I need to figure out his height. Well, if they are going to have an equal amount of energy at the end of their jump, I can set those two values equal to each other. So in order to solve for height, I have to take the nearly 4,000 joules and divide by the 9.8 and also divide by 102, and that gives me a height of 4. I would actually have 3 sig figs there. So he needs 4.00 meter height. He's jumping from a 3-meter platform, which means if I take the 4.00 meter height that he needs, subtract the 3.00 meter height that he began with, that gives him a total jump of 1.00 meters.
So today we're going to be looking at collisions. Collisions can be complicated, but one of the things that we want to make sure we keep in mind is that energy is always conserved, although it may not be conserved in the same form. And secondly, that momentum is always conserved. Remember, momentum is mass times velocity. We're going to look at 3 different cases of collisions. In case 1, I'm going to call this reverberation. So we have 2 carts that collide. The first cart that was initially moving bounces backward. If we look at the momentums, initially I have cart C, which has a 1 kilogram mass moving at 1 meter per second. So it has 1 unit of momentum. When it strikes cart D, which also has a 1 kilogram mass but was not moving, what ends up happening is cart C bounces backward, so it has a negative zero point 0.2 momentum, whereas cart D moves forward. Its mass is 1 times the 1.2 meters per second that it is traveling. It now has 1.2 momentums. We combine those and we get what we started out with, which was 1 unit of momentum. So that's case 1 where we have reverberation. In case 2, it transfers all of the energy. So we have that initial 1 unit of momentum coming in from cart C. Cart C hits cart D and then stops. So its momentum is now 0. However, cart D, which weighs 1 kilogram, is now moving at 1 meter per second. So it has a total momentum of 1. In the third case, we're going to combine the two where the 2 carts stick together after the collision. So we have an initial momentum of 1. When the 2 carts strike together, they now have a combined mass of 2 kilograms. However, they're only moving at a half meter per second. So we still have a total momentum of 1. Now that brings us to the topic of the kinetic energy. What about the kinetic energy in each of these cases? Is it conserved? Well, let's take a look at case 1. Our initial kinetic energy in case 1, where we have a 1 kilogram mass moving at 1 meter per second, I have a half a joule of energy. Remember, kinetic energy is 1/2 the mass times the velocity squared. After the collision, I have a total of 0.02 joules of energy from cart C, because we have 1/2 of our mass, so a half a kilogram, times its velocity, which is a negative zero point 0.2, but that's going to be squared. When I square it, it becomes positive. And we also have 0.04 now. So if I multiply those two together, I get a total of 0.02 joules of energy. Cart D, which has a mass of 1 kilogram, so if we take 1/2 times its velocity squared, 1.2 squared is 1.44. We multiply by our half kilogram, the mass, that gives me a total of 0.72 joules. So total, I have a 0.74 joules of energy. Somewhere along the way, I have gained 0.24 joules of energy. In case 2, what we call an elastic collision, our kinetic energy is conserved. We had a half joule of energy before the collision. After the collision, we still have a half joule of energy being seen. And that brings us to case 3, which is what we consider an inelastic collision. My initial amount of kinetic energy was 1/2. After the collision, I now have a combined mass of 2 kilograms. Half of that would be 1 kilogram. But my carts are only moving at a half meter per second. So when I square that velocity, I get 0.25. 0.25 times 1 is 0.25 joules. So somewhere along the way, I've lost 0.25 joules worth of energy. So now let's take a look at the example problem 3. In an accident on a slippery road, a compact car with a mass of 575 kilograms moving at 15 meters per second smashes into the rear end of a car with a mass of 1574 kilograms, moving at 5.00 meters per second in the same direction. What is the final velocity if the wrecked cars lock together? And then part B, how much kinetic energy is lost in the collision, and what fraction of the original kinetic energy was indeed lost. So if we take a look at what we know the mass of the two vehicles, we know the speed of the two vehicles and that they're going in the same direction, and we know that at the end they are going to be connected. Let's begin by finding the final velocity. So I have my initial momentum of car A plus my initial momentum of car B has to be equal to the final momentums added together. In this particular case, since they are stuck together, I can just add their masses and I know they're traveling at the same speed. So solving for the final velocity, I end up getting 7.67 meters per second. Now let's determine the change in that kinetic energy of the system. So my final kinetic energy would be 1/2 times the sum of their masses, since they are stuck together, times their final velocity squared. Working that out, I get a final kinetic energy of 63,200 joules. Now I'll take a look at my initial kinetic energies. My initial kinetic energy of the first car is going to be 1/2 times its mass of 575 times its velocity of 15.0 meters per second squared. And then I'll add in the 1/2 of the mass of the second vehicle times its velocity of 5 meters squared. That gives me an initial kinetic energy of 84,400 joules. So what was the change in my kinetic energy? That would be a change of 21,200 joules in the negative. What fraction of that is of the total original kinetic energy? Well, if I take my loss and I divide by my original kinetic energy of the 84,400, I get roughly 25.1% of the original energy that was in kinetic form was lost to some other form of energy. You may wonder, well, what other forms of energy would there be? Well, you have sound, you have the energy now in the metal that is crunched and bent. That took energy in order for that to happen. So there are several forms of energy that is lost, so to speak, in the collision. So as we look at the differences in momentum versus the energy, you can think of momentum causing the objects to either change speeds, directions, or even to stop. So for instance, a 10 kilogram object traveling at 5 meters per second can stop a 20 kilogram object traveling at 2.5 meters per second in the opposite direction. However, their energies are not the same. The lighter object has more kinetic energy. It has 125 joules worth of energy as opposed to only the 62.5 joules of energy of the heavier object. Because kinetic energy, you are squaring the velocity. So the velocity has a much greater effect on the energy amounts than the mass does. It takes more energy to get the smaller object to acquire the same amount of momentum. So a small compact car getting up to 60 miles per hour takes more energy than, say, for instance, a semi truck that's fully loaded getting up to maybe 10 miles an hour. They may have equal amount of momentum, but the amount of energy needed in order to get to that point is much different. In a car wreck, momentum is what's going to stop the vehicles. The energy is what is causing most of the damage. The crinkling of the metal, those types of aspects is where the energy is now being released in some other form. Now let's take a look at another scenario. Let's just say we had two objects that were close together where a spring is in between them, and that spring is compressed. So it has some potential energy in what we call elastic potential energy. When it releases its energy, the objects are going to move away from each other. Now, if the objects have equal masses, they should move at equal speeds. If they have different masses, they are going to move at different speeds. However, their momentums are going to be the same. As an example, let's say I have a 1 kilogram object and a 5 kilogram object. If I put enough energy where that 1 kilogram object is moving at, let's say, 10 meters per second, it has a momentum of 10. That means the other object is going to be moving at 2 meters per second, so that it also has a momentum of 10. However, the energies are going to be drastically different. The 1 kilogram object traveling at 10 meters per second has 100 joules worth of energy in it. However, the 5 kilogram object moving at 2 meters per second only has 20 joules worth of energy in it. So even though they have the same momentums, they have drastically different kinetic energies. Let's take a look at one of your homework problems.
So an 8-gram bullet is fired horizontally into a 9-kilogram block of wood on an air table and is embedded in it. After the collision, the block and bullet slide along the frictionless surface together with a speed of 10 centimeters per second. What was the initial speed of the bullet? So I've listed down what we know, and I've converted it into our standard units. So I took the mass of our projectile, or our bullet, and made it, instead of 8 grams, I made it 0.00800 kilograms. The mass of the block of wood was already in our standard unit of kilograms, and then the velocity they gave me as 10 centimeters per second. Well, I changed that to be 0.100 meters per second. Now, to find the velocities, I know my initial momentum of my bullet has to be equal to the final momentum of my bullet and block combination. So my initial momentum of my bullet is going to be its mass, which is 0.00800 kilograms, times its velocity, which I do not know. And that is going to be equal to my final momentum of addition of the two objects' masses, which is going to be 9.00800, where my last sig fig is actually the second zero after the 9, times its final velocity of 0.100 meters per second. So when I divide both sides by the 0.00800, I have 3 sig figs on this side, I have 3 sig figs on this side, 3 sig figs here, so I'm going to need 3 significant digits in my final answer. Well, I get 112.6, and that is going to be, since the kilograms canceled out, meters per second. So with only 3 sig figs, that gives me a total of 113 meters per second as my final answer.